Okay, these guidelines over here for graphing rational functions come from a pre-calculus book. And they're good guidelines to follow until you reach the point where you want to extend that using first derivative, second derivative tests, tests for concavity and all that. So let's quickly go through these, just so you can see the steps make sense to go through. Find the x-intercepts. That is all the real zeros of the numerator. This function will equal 0. Y will equal 0 when the numerator is 0. That's when x equals 5. 1, 2, 3, 4, 5. So there's a point on the curve right there. And x is 5. Y is 0. Find the real zeros of the denominator. Well, the denominator only equals 0 when x squared equals 0 or x equals 0. That means that the function is undefined when x is 0, so we have a vertical asymptote. The only one. Third, find the y-intercept. When x equals 0, what does y equal? When x is 0, we're undefined, so there is no y-intercept. Apply the theorem on horizontal asymptotes. When we have a rational function, if the degree of the denominator is larger than the degree of the numerator, then the horizontal asymptote is always the line y equals 0. Okay. If there is a horizontal asymptote, and there is, determine whether the graph actually crosses the horizontal asymptote. And we want to know, does x minus 5 over x squared, does that ever equal 0? And we know for a fact that that only happens right here at x equals 5. So indeed, this graph does cross its horizontal asymptote, but that's the only place where it happens. Sketch the graph of each of, well, okay, now this is where we're going to start using calculus. Okay, let's go to the next board and see what the graph looks like. There's the vertical asymptote, the horizontal asymptote. It looks like there is a critical number here at 10 when x is 10, and of course when x equals 0. Let's go to the next board and we'll talk about that. So I'll just use y equals x minus 5 over x squared. So y prime is equal, use the quotient rule, denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared, which is x to the 4th. And we can simplify that if you want. So we'll get x squared, then we'll get minus 2x to the 3rd, and we'll get plus 10x all over, oh, sorry, that should have been x squared cubed. All over x to the 4th, we get, should have been x squared, I wrote x cubed again. We get minus x squared plus 10x over x to the 4th. We can factor out an x and cancel. So we'll get minus, I factored out a minus. And then the x cancels. So for sure, the critical numbers are x equals 0 because that's where the first derivative is undefined, and also at x equals 10. And if we go to a little number line, if I put 0 on here, I might put x right here to indicate that that's a vertical asymptote. The function's not defined there. And at 10, we want to know what is the sign of the first derivative, which will give us information about the original function. So to the left of 0, like -1, let's put a -1 in here and see we get a positive or a negative number. We get -11, yeah, 11 divided by negative, okay? So the function is decreasing to the left of 0. Between 0 and 10, put a 2 in here. 2 minus 10 is negative 8. Opposite of negative 8 is 8. 8 over 8, positive, increasing. And to the right of 10, like an 11, we get negative, decreasing. Okay, now there's not a relative minimum here because the function's undefined there. The function does go from decreasing to increasing at x equals 0. And it crosses there, but then it starts coming back around down. And at 10, we reach a relative maximum. And this table, back on board 2, shows you that. Here's the relative maximum at x equals 10. As we go to 11, oops, that's supposed to be a 12. These values get smaller, and if I'm to the left of 10, they're still below the 0.05. So in the vicinity of 10, the highest y value is 0.05. Okay, now I could do the second derivative test.